session on logic gates. Today we are going to cover the logic gates you have to learn in order to pass your A-level computing. So, without further ado, these are logic gates. A and B are inputs, Y is an output on each one of these. Now each one of these symbols means something different and a different name. This is an AND gate, an OR gate, a NOT gate, a NAND gate and a NOR gate. What do they mean? How do they work? Well, let's find out. So, to start with, an AND gate. AND gates, you must have both of these two, must have a charge in before Y will equal 1. So down here, this is called a truth table. This tells you what will be output depending on the input. So both inputs 0, the gate's like, nope, I'm an AND gate, we must have both of you as 1. You go, okay, I'll give you 1 as 1 as 0. How about that? Bit of negotiation, it might work. Nope, not happening, says the AND gate. We must have both. So, swapping round, A is 0, B is 1. Nope, Y is still 0 because it needs both of them to be working. However, if both are 1, then Y is 1, as the truth table says down here. So, AND gates, both of them must be working. However, there is a more relaxed version of this gate, and that's called an OR gate. An OR gate will accept either or both, A or B being 1, to work properly. So, A and B both 0, well, Y is 0, nothing out of Y, nothing going in. If A is 0, B is 1, Y is 1, it takes either, it's happy. If A is 1, B is 0, again it outputs 1, it's happy. And if both of them are there, A is 1 and B is 1, again that's both of them, it's very happy, doubly happy, so Y equals 1 again. Nice and simple. Now, the next one is a NOT gate. Now NOT gates are a bit of a tease. If A is equal to 1, then Y becomes 0. But equally, if A is equal to 0, then Y is equal to 1. Basically, it just swaps around whatever you give it. Frustrating, irritating, possibly, but you can have fun with it too, I think. So, now we have two more gates to look at quickly. A NAND gate and a NOR gate. These are basically AND gates followed by a NOT gate. Little circle here in front of them means NOT gate as well. So you've got AND gate, an OR gate, and a NOT gate straight afterwards. So, how would that work? Well, this is for the NAND gate. So the NAND gate says if the AND gate outputs 1, then I've got to output 0. Otherwise, if the AND gate outputs 0, I can output 1. So, A and B, well, A and B both being 0, the AND gate outputs 0, so the Y gate, the NOT gate will output 1. Perfect. Next one. Input A is 0, input B is 1. Okay, so the AND gate outputs 0, because it's not both of them. So the NOT gate, taking a 0, will output a 1. So now Y is equal to 1. The same stuff around, but if both of these are 1, the AND gate says, hey, yes, out goes a 1. And then the NOT gate goes, oh no, turn that right around now, and puts out a 0, so there is no output. For NOR gates, it's slightly more interesting. So if an OR gate and a NOT gate, so if the OR gate puts out 0, the NOT gate puts out 1. If the OR gate puts out 1, then the NOT gate puts out a 0. How does it work? Well, let's see. A is 0, B is 0. Well, the OR gate is not going to anything out for that, it's going to be a 0. So the NOT gate will send out a 1. Input A, input B, 0, 1. Well, that will put out a 1. So the NOT gate reverses it, it becomes a 0. Same here, A1, B0, and A1, B1. So, those guys are simple transistors, or logic gates, as we call them in computing. How do they work? Why is this stuff important, you're thinking now? Well, you can design huge circuits and huge systems using these gates and these principles. How does it work, you're asking, I'm sure? Well, this is an example of a logic gate circuit. So say I had got 4 inputs and I wanted to only proceed if they met the right criteria. So A and B, not C, and D with the others. Again, guys, that is starting to get seriously complicated. How so? Well, we'll learn all about this next lesson. So, today, guys, we have learnt about AND gates, NOT gates, and OR gates. Not to mention NAND gates and NOR gates. Thank you very much for listening. Good luck with the worksheet, and